Okay, so let's heat up water, okay? And to do that, we're going to use MCAT. This is actually going to be our sort of our work output will be that, right? Okay, the work input, the total energy in, is going to be the energy we get from burning the natural gas, okay? So that's going to be the energy that we get from some mass times some specific energy. Now notice that we're using natural gas here. Okay, so our specific energy for natural gas is going to be 55 times 10 to the 6th joules for every kilogram. So if we know how much mass or how much energy we need, we just divide by this, and that'll give us the mass of natural gas we need to burn. Okay, now let's do this twice. The first time, let's make it a 100% efficient water heater. Okay, and I'll just show you what that means, right? So at 100% efficiency, all of the energy that we burn turns into the heat that goes into the water. And this is not realistic because in reality, a water heater has to, heat has to go up the flue for most water heaters, right? But if you have a super efficient water heater, not much heat goes up the flue. So they have a little fan that kind of blows all the carbon monoxide and bad stuff out of your house. Okay, but let's just pretend it's 100% efficient, right? Well, the energy we need, okay, is just going to be the heat, right? And the heat is MCAT. So that's going to be 195 kilograms, because a liter is a kilogram, right? Times 4186. And this is joules to raise 1 kilogram, 1 degree Celsius. But we're not raising 1 kilogram, we're raising 195. And we're not raising it 1 degree Celsius, we're raising it 44, is that right? Degrees Celsius. So let's figure out the heat needed. 195 times 4186 times left parenthesis 59 minus 15. So the energy needed is 35,915,880 joules. Now, if it's 100% efficient, that's the energy we need, right? Because all the heat coming from the burning natural gas goes into this, which normally isn't the case, but let's go with it, right? Okay, so that's our energy needed. And then we just say, okay, well, if E equals, if the energy is M times the specific energy, if the energy equals M times the specific energy, then the mass is the energy divided by the specific energy. So I'm just going to take that and divide by the 55 times 10 to the 6th, and that's joules per kilogram, right? That's going to equal our mass. So let's do that. So this guy divided by 55E6 gives us the first mass here, okay? So the mass, if it's 100% efficient, you would only have to burn 0.0653 kilograms. Okay. Now, this number here, we're going to use this again, and we'll use this again. But now let's look at it if it's 56% efficient. Okay? I'm going to erase here in 3, 2, 1. Okay, so now it's 56% efficient. Okay. Well, the only difference now is if we do MCAT, right? The heat we need is MCAT. So 195 times 4186 times 59 minus 15, which is 44, right? That's just this minus this. That is still 35,915,880 joules, okay? But that is our output, right? That's going to be our output. We want to know what the input energy is, because the input energy is what comes from the burning the natural gas, Okay, so the efficiency is output over input. So therefore, input is output over the efficiency, right? So it's going to be this 35,915,880 divided by, what is it, 56, so divided by 0.56. So divide by 0.56, and that is 64 million. So now we need more energy is what I'm saying. 64,135,500 joules, right? That's the energy we now need to get from natural gas. So the mass is going to be energy divided by specific energy, 64,135,500. And now we're getting that from natural gas, right? And that's joules that we need divided by 55. And this is joules per kilogram. And of course, that'll end up being kilograms. So divided by 55 is 6, and that is 1.1661 kilograms, or about 1.17 kilograms. All right. There you go. And in the next video, I'll show you how to deal with like thermal power generation plants.